There we go. There we go. Okay. Oops. I need to turn this down. What does this sound like? Let's hear. Alright. We are chilling. Median of two sorted arrays. Alright, let's go. It's binary search. So, just want to be able to explain this one because I can't right now. Shrink this. What time is it? 7:20. Yeah, it's close enough. Okay. Okay. So the whole point is like, yeah. Wait, whoa. This is not the problem. This is. So the whole point of this is you just partition the arrays. My understanding is you partition the arrays and dynamically finds the the middle of the two arrays. Because they're both sorted, because both of the arrays are sorted, so you can just get the length of both of them. Find that midway point between both of them. And then you take the middle of nums1, subtract it by the middle of both. Okay, actually, so let me explain that. See, this is why I need to do this, because I have to double, triple, quadruple tick. So the whole point is, because both of these arrays are sorted, you can take the total length and then find the total midway point, and then you'll binary search through the shorter of the two arrays, whichever one that would be, and you find the midway point of that shorter array, and subtract the total midway point by that to find your second partition in the second array. Using that, insofar as the partitions in both arrays satisfy the binary or the sorted condition, insofar as that is the case, then we have our median. But I don't know exactly why we do a particular portion of this. So you can do like int length 1 equals nums1.length, int length 2 equals nums2.length. If length 1 is greater than length 2, we're going to return find median sorted arrays for nums2 and nums1. So now you do int left equals 0, int right equals nums1. I don't know why we don't do nums1 minus 1. See? Why? And then we have int half equals, or total length. Total length equals length 1 plus length 2. Int half equals total length plus 1 divided by 2. And we want to truncate it. That's why we do plus 1. So we want to round up, basically. And then while left is less than right, int partition 1 equals left plus right minus left divided by 2. Int partition 2 equals half minus partition 1. So, shoot. Okay, so left 1 will equal partition 1 equals 0. Integer dot min value. Otherwise, partition, or what? Nums1 partition 1 minus 1. So, yeah, I should probably explain what we're doing. So we need a left and a right pointer, and then we need to calculate our total length and the half, and then we will binary search. So here is where we create our partitions. So we get the half waypoint between nums1, for nums1, which is the left plus right minus left divided by 2. And then we get the remainder of the total half by subtracting partition 1 from the total half. So then we need to establish our partition, what do you call them? Our adjacent values to the partition, because the partition isn't on a particular value. It's just splitting up an array in the middle. Like, it should be where a comma is, right? So that's the only place we can place our partitions. But we need to find the adjacent values to be able to determine if both of the partitions are satisfying the sorted condition of both arrays. So we have int left 1. If partition 1 equals 0, right? So if our first partition's all the way at the very front, we're going to want to imply a temporary negative infinity. Because there's no other value in that current array that will be able to go below 1 in this case, right? Or actually it'll be 2 because nums2 is the lower one when we recursively return this. So yeah, there's nothing before 2. There's actually nothing after 2 as well. So I'll get into that scenario as well. So here we'll have int right 1, which will equal partition 1. Or we'll see if partition 1 equals nums1, so the length of nums1. And if it does, we're going to set it to integer.max value. And otherwise, we're going to take the partition and get the value of it. And we're going to do the same for the second partition. Partition 2 equals 0. Integer min value nums1 2 dot partition 2 minus 1 int right 2 partition 2 max value is 2 partition 2 minus 1. Okay, so if left 1 is less than or equal to right 2 and left 2 is less than or equal to right 1, then we have satisfied our sorted condition. And we want to compare left 1 and left 2 to right 2 and right 1, because we want to basically cross-reference the partition adjacents to each other to ensure that they're less than or equal to each other. And that's exactly what this is doing. So yeah. Now, there are two scenarios that will occur when we have hit our partition, the the ideal partition. So if the total length of our input arrays is odd, so if we mod it by 2 and it equals, actually let's do even, and it equals 0, so if it's even, we are going to need to take the max of the lefts and the minimums of the rights, or the minimum, sorry, singular, of the rights, and find the median of them. Because if we have an even amount of numbers, the median is between 2 and 3, so it's 2.5, right? So the answer will depend on the total length of the sum of the input arrays. So here we're going to return, I'm going to cast this double, or actually we don't even need to cast this. So we're going to turn math.max, actually we probably should, double math.max of left 1 and left 2 plus math.max of right 1, or math.min of right 1, right 2, and we actually do not need to cast. Let me do this. And we just divide by 2.0, right? So that will get us our even. Now for our odd, we just want the max of the left. So this I'll probably type cast, but it'll be math.max left 1, left 2, and that will be our answer. Now, if left 1 is greater than right 2, then we want to increase the partition 1. Decrease the partition 1, because one of our lefts, the partition 1 left pointer, is too large. So to do that, we're going to set right to equal partition 1 minus 1, because that will close the window from, let's say, 1 and 3 to just 1. So we are making our options for the binary search smaller. And then we'll do the opposite for the other case. And then we'll return 0.0, which is kind of like an exit condition. Yeah, let's... Oh. I do kind of want this. Oh my gosh. What am I, dumb? Partition. Oh my gosh, I did this completely wrong. What the heck? Length 1. This is why I need to restart length 2. Do we not need this? Oh, yeah. Isn't it like this? Maybe it's like this. There we go. See, I don't know why we do that either. How do I solve that? Jeez. I literally don't know what I'm doing wrong. It looks the same to me. Wait. Oh my gosh. That's it. Incorrect. This line actually is correct, brother. Okay. I need to go bathroom. I need to change something. So then we're going to do the same for the right, or sorry, the second array. And it's literally identical. Min value, partition 1, length 2 minus 1, right 2 equals partition 2 equals length 2, got max value, partition 2, length 2. So if left 1 is less than or equal to right 2 and left 2 is less than or equal to right 1, then if total, so if we've satisfied the binary search condition, or sorry, this sorted condition across both of the arrays, then we will return our answer, and our answer will be dependent on whether the total length is even or odd. So if it's even, we're going to return the average of the two middle values right here. And then if it's odd, we're obviously just going to return the middle number, because that's how medians work. So we're going to take the max of the left 1 and left 2, and we're going to add the min of right 1 and right 2. We're going to divide by 2.0 if it's even, and if it's odd, we're going to return just the max of the left 1 or left 2. So yeah, if we do not satisfy the sorted conditions, if left 1 is greater than right 2, then we want to make the left 1 smaller. So we're going to make right equal to partition 1 minus 1. And then if left 1 is less than right 2, then we want to make it bigger. So we're going to make left equal partition 1 plus 1. And then otherwise we're going to turn 0.0, which is our exit condition. Oh, shoot. Nums 1. I'm so dumb. One. I think I get it now, though. Oh my gosh. This is 2. Okay. So my guess, not my guess, but my educated guess is, now that I'm looking at it, this makes a lot more sense. So partition 1, I wish they gave us like more options. So partition 1, let's say it's here, right? It's pointed at 0. It would be pointed at 0 right now, I think. 0 length 1 is 2. So 0 plus 2 minus 0 divided by 2 is 1. So it's actually here. Wait, but no, partition 1 is 2 right now. So it's 0, 1. 1 divided by 2 is 0, so it's right here. So partition 1. Okay. This is a bad example. That's why I need a larger one. So basically, we have the partitions, right? The partition will equal... there's a partition value and then a partition minus 1 value. So this is left. So this is... Or sorry, this is right. This is left. which is exactly how it's labeled, which I guess I didn't get before. But basically, the partition will point at one value, but we want the value before it to be able to compare to the value before the second partition. So this is just a left and right pointer for the partition, and then if it's 0, it's min value. It's a theoretical infinite minimum. If it's the length, it's a theoretical length maximum. Oh shoot. It's a theoretical length maximum. So yeah, that actually makes more sense than I initially thought. Dude, streaming really cooks your computer hardware. Jeez. Same with left, same with right. So I get why we do this now. So if it equals 0, we're gonna have min val. Yeah. So if we ever get to an extreme end, either the beginning or the end as the partition, then we'll have these values and they will always satisfy these conditions. So we've exhausted all the possible options, basically. That makes sense. So then why do we do this? I get all of this. We do -1 and +1 because A, we have less than or equal to, and we would run into infinite loops, and B, because we know partition 1 doesn't work because of these two conditions. Jeez. So why do we do this? Oh, jeez. How about a sneeze? What? I have comments like, why on lines that I do not fully understand. Can you explain why each line is important to the algorithm? Okay, I don't really get this. Yeah. Okay, I had a feeling that this allows us to, this allows us to close in on the median. And I have a feeling that this is so that we can get the max infinite. does int right equal us to have the in the event that we exhaust all the options. Okay, so that's why we have that. Oh. Do we do int half equals total length plus 1 divided by 2 to provide the left partition with the odd value, so that whenever we have an odd total length, we can just return math.max left 1 left 2? Does it just ensure that the median, when all conditions are satisfied, stays in the on the left side? Oh, okay. I get that now. Okay. Cool. Let's do it one more time, just so I know. So, to solve this, we basically, firstly, to solve this, we want to use binary search, a modified form of binary search. And we would want to run it, we're only going to run it on the first array. So we want to ensure that the first array is always small, or the smaller of the two, sorry. That's the first thing. Second thing is we are going to basically create a partition for the first array and a partition for the second array. And using those partitions, we'll find their adjacent values and compare them to each other. To determine whether we have found the we'll compare them to each other basically to determine the middle of both arrays. So you can take this array, for example, these two arrays, for example, and append them together. We have 1, 3, and then 2. And we can shift our partitions that we have on these values to the point where each partition points to the overall center of both of the arrays. And based off of the adjacent values and whether they satisfy the sort condition in these arrays, we can determine what is the median. So how that looks like is we have length 1 equals nums1.length, and then length 2 equals nums2.length. If length 1 is greater than length 2, we're going to return find median sorted arrays, but with nums2 and nums1, with the arrays swapped. Then we're going to get all the information we need for our binary search. We're going to make the left pointer equal to 0 and the right pointer equal to length 1. Traditionally with binary search, you do something like length 1 minus 1, but we don't do that here because of a condition that I'll explain later on. And then we need to calculate our total length, which is equal to length 1 plus length 2. And then we need to calculate our overall half between both of the arrays. So half will equal total length plus 1 minus divided by 2. And the reason why we do this plus 1 is we want to round the half a halfway point up one by one to be able to provide the left half, the left half of our partition the odd number. And that'll come into play when I write the logic. So while left is less than or equal to right, we want to create the first partitions. So partition 1 will equal left plus right minus left divided by 2, which is the halfway point between left and right. And then partition 2 will equal the total half minus partition 1. So both of these will always add up to half, which is important, right? We always want to maintain half of the array. So now that we have our partitions, we're going to find our adjacent values for each of the partitions, partition 1 and 2. And to do that, we're going to calculate left 1 and right 1, and then left 2 and right 2, like so. Left 1's calculated, left 1 and left 2, these will be, the lefts and the rights here will be calculated the same, just with the different partitions. So left 1 will equal partition 1, will equal a value based on whether partition 1 equals 0. If partition 1 equals 0, we are going to set it to a theoretically small, like infinitely small value, which is integer.min value. And the reason why we have this is because there are instances where there can be instances where nums2 has, let's say, let me think of a scenario. Let's say nums2 has a ton of small values and nums1 has a ton of large values that far exceed these values. So if we had something like, if this was nums1, this was nums2, if we had something like 10, 20, 30, and 2 was 1, 2, 3, right? If this was the case, our binary search algorithm would point to 20 and then say, okay, this is way too big, point to 10 and say, this is way too big, and now what? So we need to be able to have a pointer here, which is like negative infinity or whatever, and the same is over here too. So that's what I'll write that logic into the right pointer as well. But it's important to remember that we need to be able to, if we have a situation where one array is way bigger than the other array, we need to be able to account for values that aren't necessarily within the array to continue the binary search logic. So if partition 1 equals 0, we're going to make a infinitely small value, and then if it's not equal to 0, we're going to just grab nums1 partition 1 minus 1. So what is right before the partition? If partition 1 equals length 1, then we are going to do integer.max value. Because as I showed in that little graph, we want something to the upper end as well as the lower end to be able to account for values that aren't necessarily in the array. So here we'll do nums1 partition 1. So this is, we have a partition, we grab the value there, and then we grab the value directly before it. So we have 2 pointers basically right here. And we're going to do the same thing with left 2 and right 2, but with partition 2. So if partition 2 equals 0, we're going to make it integer.min value, and then nums2 partition 2 minus 1. And then here, partition 2 equals length 2, integer.max value, if that's the case, and then nums2 partition 2. Okay, perfect. So now we have each of our partitions and the adjacent values at those partitions. and we can determine whether or not these partitions satisfy the sorted condition across both of these arrays based on whether left 1 is less than or equal to right 2 and left 2 is less than or equal to right 1. So we're basically cross-referencing these values. And if they satisfy these conditions, then we have found two partitions where two middle points across both nums1 and nums2 that allow us to know which values are in the middle between the two arrays. So if this is the case, we have identified variables that allow us to determine what is the median of the array. Now, if the median, or if the total length of the array is even, we have to make a calculation like so, where you grab the average between the two values, because the median is the middle value, right? But we have to be able to make this calculation. And if it's odd, then we obviously just grab the odd numbered value in the center. But we're going to return the max between left 1 and left 2, add that to the minimum of right 1 and right 2, and divide by 2.0 to make it a double. And then if it's odd, then we will just return math.max left 1 and left 2. And this is where the half calculation comes into play, because what this roundup does is it ensures that if we do have an odd numbered or an odd total length, if we do have an odd total length, this roundup calculation ensures that the median will always be placed in the left partition, on the left side, basically, between the two arrays. So that's why we need to make that roundup calculation here. Cool. So now we have our median. If we don't have our median, we have to make some adjustments, right? We have to binary search. So else if left 1 is greater than right 2, we know that we need to make left 1 smaller to be able to satisfy the sort condition across both arrays. So to make left 1 smaller, we have to make right equal the partition 1 minus 1. And then we do the opposite, partition 1 plus left equals partition 1 plus 1, when left 1 is smaller than right 1, because that means left 2 needs to be bigger, right? So left 2 needs to be bigger, or left 1 needs to be smaller, right? So that's what we do. And then we return 0.0. This line will never reached, because we'll be able to find it no matter what. It took me 50 minutes I think I did a pretty good job explaining that, but it took me 50 minutes to be able to even understand this, Johnson. Oh my gosh. Okay. Longest substring without repeating characters. Where is that? Is that sliding window? I guarantee you I'll be able to explain this if I get it. For int right equals 0, right has to be less than s dot length, right plus plus. And then we need to make a map of integer map equals new hash map. So if map.contains key cur char cur equals s.char at right, left equals math.max left map.get cur plus 1. Otherwise, map.put cur right, and then into output equals 0. Output equals map.max. Output right minus left plus 1. Turn output, something like this. Yeah, it's getting to the point where I just know how to do these. I don't even know why they work. Is this a medium? It is. It's the third problem ever, too. Wow. Okay. Okay, let's see. Let's see how this works exactly. Okay, so we have something like this. A, B, C, A. We encounter a duplicate, okay? So left is currently 0. Left equals 0. So left is going to equal math.max left, or this plus 1. And the reason why we do that is because we're going to add this now, and then we're going to remove this. We don't want to consider the duplicate that we just ran into. So this will be 1. I don't get what the plus 1 was for, that's why. So BCA, B, boom, same thing. We ran into B. So left is now moving to 3. No, 2. Yeah. So now we have cab, C, boom, same thing, 3. ABC, B, boom. Now it's left is this, plus 1. So A, B, C, B, 1, 0, 1, 2, 3, 4, 5. Left is now 5. Okay, so the reason why we do plus, I didn't understand why we did plus 1 here. So the reason why we do plus 1 is because when we encounter a duplicate, we want to get its oldest duplicate plus 1, or the current pointer of left, whichever one is greater. But I don't know what situations is left greater than cur. Oh, situations where let's see. So we're here. Yeah, it's kind of hard. Which situations does that occur? Which situation? What's the weather like today, actually? Nice. Oh, so this would happen. Left would be greater than map.getCurs if we had something like, I think let's do this. Yeah, something like ABBA, I think. So we would have A, B, and then we would encounter another B. So then boom, left is now equal to this B, which is 2. And then we run it to be A, but map already contains A, but A is all the way back here and we already skipped it. So that's what would happen. So it's if we've run into a duplicate that skips a potential new duplicate that is before the old duplicate. That's the only way I can explain it. Right minus left plus 1. I think this is just because it's 0 indexed. So it's like 3. If we do ABC, it's 2 minus 0 plus 1. Yeah. If we do BCA, then it's... if we do BCA, then it's 3 minus 1, which is 2 plus 1. Yeah, so it's just 0 indexing there. Okay, cool. That is cool. That's an hour in the morning. Not bad, not bad. It's nice to get this stuff done out the way. Oh wait, let me go here. This is... yeah, not too bad. My arm is messed up.